315, count of smaller numbers after self. You're given an integer array nums. You have to return new counts array. The count array has the property where count sub I is the number of smaller elements to the right of numbers sub I. Okay. Uh, hmm. My intuition is that there's some sort of stack things here. No, maybe not. Let me think about this for a second. This is a very easy to read problem, at least, and not a tricky thing. I think also would have been nice to know what the n is, but that's maybe fine. Um, hmm, right now, I'm just thinking whether there are ways to abuse, or maybe not abuse. Abuse is a big word, but just some way to figure out how to use some sort of prefix or suffix sum. Another thing I'm thinking about is maybe some sort of log n data structure, like some sort of what you might call it, like some sort of tree essentially. Uh, but let's see what happens if there's a tree. Let's say you have five and then two. Um, but I think there's a yes, yeah, there are a couple of trees like segment trees. But I'm just thinking about it in general. Because to be honest, I am not as familiar in segment tree as a lot of people are these days. It was not as common when I was younger to know about segment trees. But hmm. Mm, wonder if there's a way to kind of. I mean, I guess that kind of is like a segment tree where. Well, there is some sort of. Hmm, I want to say that there is some sort of like what you call it. Um, I mean, well, clearly there's an n square algorithm, so probably n square is not gonna be good enough if it's a hard. Um, so next thing I would think about is n log n. Um, and what's in that class of n log n um, n log n problems, right? Maybe some, and that is yeah relating to something I was thinking about, just like some sort of longest, some sort of thing that's related to longest increasing subsequence. I mean, obviously it's not going to be increasing in this case. Maybe not, but maybe going backwards. But five is one. We're going backwards. Uh, six, and then some sort of tree makes sense though. Okay, six. Yeah, maybe friend with tree is the way to go because oh yeah, maybe. Hmm. Also, kind of reminds me a little bit of Cartesian trees with stacks, but that's don't know how I get it here. I feel like it's a standard-ish or like hmm. It's two. You point to the one. What is the? Is it strictly smaller? I guess. I guess strictly smaller. There's no uniqueness or anything. Constraints. No notes. So okay. So I'm going to assume that it doesn't have to be unique, and it's strictly lower, right? Then fine. Go backwards. Well, 1 is always going to be 0, and then 6. Yeah, I think segment tree, maybe. Where you just keep on. How many? Okay. How would I create? Okay, so then 1, and then. How do I do the? I'm also trying to think a little bit about how to do things in Python easier. Like you could, if there's a way to maybe like what's it called? Like ordered map in C++. I think like you could just do the what's it called, lower bound, right? And then maybe the lower bound you could kind of do it that way to do the math. C++. Lower bound. Right. And I think you could use something like, yeah, though in this case it'll be reversed, but I'm going to do C++. Maybe I'm going to play around with that on using lower bound and an ordered map. Because then you get the log n query. Yeah, okay, we'll play around with that. Okay. Oh, actually I want to reverse this. Let's figure out how to do it. Okay. Oh yeah, I have to do results. Okay. So then we just do that seems reasonable. But first we want to query the reverse the lower bound, which gets the next number that is greater than or equal to that number. So actually we want the negative of this, so we could get it in the other way. And then now we look up it's not a +1 or -1. Okay, so we want num -1, so the reverse of that should be, is that right? Okay. Something like that. Maybe reversed actually, but I just want to see if this compiles. Close-ish. Oh, because it only gets to 2. I have to do some summing to keep track of it. Okay, so that actually. Something like that. I mean, I didn't reverse yet, but I mean, I guess this is relatively easy to generate some test cases for. And I say that and I do it, but let's do a more like an obvious case. And also something with the same number. Oh no. But that number should contain all the numbers that is before it, that is what you might call it. There's 7, 5, 2. Oh. Maybe there's some weirdness here, but 24 should be 3. Why is this 1? Oh, because I do it in the other order. It should, yeah, maybe I do need a segment tree. I was trying to do something maybe weird with lower bound. But you need all the sum of that thing. I was thinking of the worst case, what I consider the worst case, but that's more related to. I think what I'm doing is very much related to LIS, but maybe that reduction in my head doesn't quite work. Yeah, haven't done segment tree, but I mean, I think even just a regular tree maybe should work. I mean, it's essentially what I do, except for I would want to, for each node would contain like all the values of the subtree, right? Something like that. Don't really have a, and you could probably. Without kind of implementing a crazy tree myself, I'm just trying to think of any existing data structure that I could use. I think actually like a regular binary tree is good enough, maybe, but or a balanced one, which requires me to create a lot of yeah. Okay, so lower bound is not enough. Is there something similar in C++? Or is this just literally like I have to implement a tree? Is segment tree even good enough? I don't know. Can I use this? No, I mean whatever hacks I am doing, it's going to be slower than yeah. But whatever I'm doing, it's going to be slower than Onaga, and there's going to be like some degenerate case with n square, and that's probably going to be too slow. That's most of my concerns. So the 24 searches for 23, but then doesn't go, because this only does in one direction. Maybe I just need to eat it up and do it. At least I didn't waste the wrong answer there. Nope, I didn't submit. Okay, maybe it's time I learn how to do segment tree really well then. It's been a while. Where's the, oh, I think one thing I'm trying to think is also whether map has like a sort of, because if it's ordered, maybe I could do something to get the offset. Is there something like that? Or am I just dreaming? It's sort of right, like, but then in that case it'll be multi-map, but that's fine. Let me play around with it. Take a look. See if that does anything. Oh, that it just gives me nonsense. Nope. Okay, for tree iterator, that's not a thing. Okay. Do multi-set. All right, let me try something real quick, actually. Just the same idea. Nope. Binary index tree. I actually don't remember binary index tree. I'm actually just looking up multi-set things. Oh well. because it does get implemented into a binary search tree, but it doesn't, I guess, let you do this. You know, all right, it's binary index tree. All right, let me Google this real quick, and I guess it's time for me to learn something new today. And maybe y'all can learn with me. Okay. I have literally not touched this in like 15 years. So, is it the thing where you take like the square root in a prefix way or something like that? In the least significant bits, like half of it in the in a layer and then the other half in another layer, or that's something else? Okay. I mean, this is a very simple zero order bits, except the least significant one. How does that even work? Yeah. This sections factor is disputed. Well, I guess I should not use this code in production, but add k to element. Okay, I mean, I think I have to do some understanding before I understand why this is the case, but okay. I mean, this is straightforward. I guess I'll play around that. Okay, I don't need C++ for this. Let's go. Okay, I think I have the idea now. So one thing I do try to do when I'm learning something new is that I'm trying to understand it and then do the coding, excuse me, independent of it. But cool. All right. Let's say, what is it? Just do x, just return x, and I actually don't know if I understand this. Bitwise is craziness, because I guess because negative of it would be the 2's complement. So, because for a second I thought it meant the inverse, which is not true because it's 2 complement. Okay, I guess that makes sense. What is? Oh, okay, fine. Index and index. No, I don't have an array set up. What do they call it usually? It's just like an index. So okay, that's why I don't remember because it's called A. But okay, let's go ahead and look up. Why not? How do I initialize this? Yeah, there are a lot of questions here. What is size? How does this even work? I guess size is just the number of bits, right? That probably makes sense. Oh, is that? We'd have to learn how to do this in a little bit, but let's just say 64 bits then. Okay. Which one is add again? I think I want to do a lookup first, actually. That's why my, was it fine? And that's just taking every bit and then summing it, right? So whatever sum is here. Use 0, and then it's just this reminds me of the XOR stuff I've been reading actually, but my size doesn't make sense. Okay, I have to figure it out. X is that? So then now, yeah, okay. Then you could keep going to the next lowest bit. Okay, and then just return, right? Yeah, this is painful. Okay, and then this is the opposite where, okay. Oh yeah, because now we want every bit to contain the value. Right, is that right? Something like that. I still don't know what the size is. Man. Yeah, how do I? Okay. Okay. I mean, now now we have a lookup. Where's the initial size? If I put I guess size is just a okay, that's not okay. Maybe +1. Yeah, maybe +1. And then, because you want to have it on the nth one, and then now we want to reverse the array. How do I do it again? First input, and then for okay. Oh, well, I guess we have to find it first. Something like that. Is that reasonable? It's really been like 10, 15 years since I've done stuff like this. I really have to. I don't, not as fundamentally sound as it is. But are these things on interview? I mean, it has to be. Well, technically, these should terminate, but this is what. Is this right in Python? I don't know how how two's complement is in Python, especially if it's a big int or something. But okay, let's just start with find first. Because this should be 0, right? Eventually. It doesn't really get print anything. It's like that on my LSP thing as well. Oh, maybe I didn't. Maybe I just implemented the tree and didn't do anything. Because okay, now let's say we have to like now we have to Fenwick tree or the binary index tree up. What does that mean? Now we have to convert this to action. I think this requires more understanding of the Fenwick tree, whatever, to do it. So basically, allows me to calculate the partial sums of the first index, right? Yeah, because we want the cumulative sum of basically from 0 to, well, can it be negatives? From 0 to 5 or something, but does it help if we reindex? Maybe we need to reindex, but yeah, because otherwise this is just weird. Because it could actually have even negative numbers, which none of this really makes sense. Okay. I was going to say lookup again, but Let's leave on the side of this. Make this unique and also sort it. So now this is in sorted order, and then of number 0 to index. That's fine, right? And then now when we get it, we want to find, actually, I have an infinite loop somewhere, probably. Can I just not add stuff for a second? Okay, so the adding is doing something weird. Oh, I use n in. I don't know if that's weird. Oh man, that's also confusing though. Hey everybody, you're still with me, but welcome to Fresh Learnings with. I mean, I guess that makes sense. If index is 0, then does it never get a bit? Do I have to one index this? I guess so. That should be okay. And then it'll never be big enough. Okay, well, you know what they say: some answer is better than no answer. I don't know if that's actually true, but okay, I also had to results tab reverse, but obviously this is wrong. Okay. Oh, this isn't right. We just want to add one number. I think this +1 because this is 0 indexed. Yep. I guess I could just put it here. Oh, what? Oops. What? No. Oh, because now define is wrong. Okay. Because it's supposed to be. Try to be too clever with this one. Okay, fine. No, I mean, actually, I like this a little bit better in that this is more specifically that it's finding all the numbers that are smaller than it. So I think I'm okay with that. Okay, that's YOLO push. What's it? Because maybe I could have done more number. Okay, cool. Yeah. I mean, I think how long did I do this one for? 40 minutes, which is I guess not bad for a hard problem that I didn't know how to do. In an algorithm that I'm not very familiar with. But yeah, definitely if you're an interviewer and you need to pull out the Wikipedia, you're probably already having trouble. Yeah, I mean, what would I say? Let's say I was an interviewer, I would say, yeah, I would start the n square algorithm, which is, I think, trivial. There's nothing about it, just two for loops. And are there that many optimizations? I feel like we could talk about the binary search tree. That's what I was kind of thinking of, but I mean, oops. Um, but if you have just like a regular binary tree, where like or binary search tree, but not necessarily balanced, then you just kind of keep track of whenever you insert an element, then you could keep track of kind of the sum of the subvalues of that tree, and then it'll allow you to kind of do things in theory log n, because because you just go through the depth. But because of you could get into degenerate situations, that would be n squared, and I'm sure that degenerate situations in the case. So I think if you do a balanced search, balanced binary search tree, then you could probably do an n log n, which is maybe fast enough. I'm not doing that on an interview. This just seems impossible. Um, yeah, so I did this. I think back in the day, we used to call it binary index tree or something. I mean, I'm sure. Uh, hmm, yeah, I don't remember when I learned about it, but yeah, using this data structure so that you could kind of figure out bit by bit. You could look at each. I mean, I mean, if you really want to learn more about it, oops, what did I click on? Well, oops, sorry, hang on. Okay, cool. Yeah, I mean, I'll link to Wikipedia article, but I'm sure that people have written more things for it about binary index trees, but yeah, but it just basically each bit it just allows you to kind of store the, like, for each value you increment, in this case one, to store the sum of each, like it kind, like you can think about it like a tree, because implicit because in each like binary number there's the 0 and the 1 will correspond to different path to take, and then you just sum up all those segments to kind of get the sum of the prefixes. But and because they're log n log n digits, once in log n update time and find time. I don't think I could explain it very well here. I probably need to do some freshen up. It's been too long. Um, but uh, but yeah, I mean, it seems like if you were familiar with it, you would get this very quickly. I don't think, or like, I don't know if I recommend. I don't know. This is one of those things, like if I was into it, these are all the things I would talk about, but not necessarily solve. To be honest, I don't even think, like, I think sometimes if you get a problem like this, you're just a little unlucky. And I think I also need to also go back to segment tree. I also know segment tree in theory, but not in implementation. And I think the first time you do anything like that, it's going to take a while. So maybe it's something that I could practice offline as well, just a little bit. But yeah, but overall, a funish problem to kind of rekindle some of the old data structures that I haven't done in a while. I don't know. I think both segment tree and Fenwick tree, or binary index trees, are kind of things in the class of things that learn if you enjoy algorithms, and if you have fun with it, and you're easy to kind of like you learn it a couple of times, or you do a couple of problems, and you're probably gonna retain it for a while. But that said, it's probably like if you were to prioritize things to learn, I would not prioritize this near the top, for example, for kind of maybe obvious reasons. Like sometimes you just have to accept that, like, in the fat tail of things, there's just gonna be some percentage of things that you just don't have time for. Like if I were to, like if I have a fixed amount of time and I have to choose between showing up on maybe dynamic programming, or maybe even like greedy algorithms, and just like be really good in explaining them, that maybe that's what I would do instead, right? Versus like what in the off chance that I'm going to see problems like this. That's what I would say. I mean, it's a hard problem, so I don't know how reasonable it is to expect. I do. I mean, I don't think I have known any of my colleagues kind of ask these kind of problems with segment trees or whatnot. But things are getting more difficult from what I'm understanding. So I don't know. Right? But yeah, not something I would prioritize. Learn if you enjoy it and have fun with it, and or if you mastered everything else. But yeah, I don't know. I mean, at least in my undergrad class, this was not taught, but I had to take grad level courses for it. But